Alright, just at the end of last video the sound cut out, so I just want to go through what I was talking about quickly. I think when the sound cut out I was talking about extrapolation and interpolation. Because the 350 is inside this data set, then it is an appropriate value to substitute into an equation, like for a line of best fit. Except 1350 would not be an appropriate value. That's extrapolating. It's too far outside the data set. But that's not the problem in this situation. Because we've got interpolation, it's not an issue. Our problem is that because our R value is so close to zero, our correlation is so weak that it's not even appropriate for us to be using a line of best fit. And this is something we talked about when preparing your projects. We want to get a couple of numerical attributes that have a sufficiently strong correlation so that you are justified in finding a line of best fit to be able to make predictions about other values. If you don't have a strong correlation close to 1 or close to -1, well then you don't have a strong enough correlation to be able to use a line of best fit as a method. And that's the problem here. I said the correlation coefficient is too close to 0, the correlation is too weak, line of best fit is not an appropriate method. Alright, number 5. So we've got a math studies project. Student's given his classmates a questionnaire to fill out. So we've got a 2x3 contingency table of observed values there. So you can see that we're dealing then with gender, again, versus subject. So those are the two classifications that we're measuring against one another. And then we've got the following is the table for the expected values. Now I'll just show you something. 1, 2, 3 things that we have to find, P, Q, and R, and it's worth 3 points. So in this situation, they're not actually requiring you to show the method for how you can calculate an expected value, although that is one way to do it, I suppose. We could figure out then that the female history students, so we'll take the female total and then the history total, and divide by the super total, which you'll see either by adding the row or by adding the column, is 100, and we'll divide by 100, and that would give you the expected value, P. But I suspect that we're going to have to do a full chi-squared test on this question anyway, as I look ahead. So why don't I just actually do the chi-squared test, and then I can look at my expected values matrix B on the calculator, and it'll show me P, Q, and R all in one step. So let's go over to matrix, and I'm going to edit matrix A. I don't need to worry about deleting matrix B. That will update itself automatically when I do a chi-squared test. Here I'm dealing with a 2 rows and 3 columns matrix. Let's put in the new values. 22, 20, and 18, and then 20, 11, and 9. And now we'll quit, and we'll say stat tests, chi-squared test. There it is, and yes, calculate. Alright. Now that I've calculated the chi-squared test, I will use these values a little bit later on, but I want to have a look at my new matrix B. You'll see it's now updated to another 2x3 matrix, so the matrix named B, and it's got these values. So I can immediately see then that P is equal to 25.2, Q is 16.8, and R is equal to 12.4. And that was quicker than calculating the expected values by hand 3 times, although I would have gotten the same answers. Right, the chi-squared test now is used to determine if the choice of subject is independent of gender at the 5% level of significance. So because they've given us the 5% level of significance, we could check, is P greater than 0.05? If it is, that means independent. So that would be one way of doing it. Since I don't know what the critical value is, oh shoot, I've said write down the critical value. darn, I shouldn't have given you that question because you're not able to find the critical values by yourself anymore. Look, I'll just give you this information for free. The critical value here is 5.991. Okay? Sorry I didn't give that to you. So, let's see. We have to state a suitable null hypothesis. So we know that the null hypothesis is that my classifications are independent. So H0, so gender and subject choice are independent factors or variables or classifications if you prefer. Show that the number of degrees of freedom is 2. So df we know is r minus 1 times c minus 1. We've got, in our case, 2 rows. So 2 minus 1 times 3 columns, 3 minus 1. That's going to be 1 times 2, so 2 degrees of freedom. That's what they asked us to show, and we've shown all of our work. Great. Write down the critical value. Sorry, I should have given that to you. The calculated value of chi-squared is 1.78. Do you accept H0? So just like we can compare our p-value to our significance level of 5%, and if it's bigger, it's independent, another way of doing it is comparing my chi-squared value to my critical value. And if chi-squared is less than, then they are independent. And that's in fact what happens here. My chi-squared value is being given as 1.78. I'm just going to double check this by looking at my stat test, chi-squared test, calculate. Let's look at that. Yeah, that's what they got too, a chi-squared value of 1.78. So my chi-squared, because it is less than 5.991, the critical value, that must mean that we do accept the null hypothesis. Okay? And that means that they are independent classifications. Gender and subject choice do not influence one another. We could have also compared our p-value to 0.05. Because p is up at 0.41, 41%, it's easily bigger than 5%. So you could say that our p-value is equal to 0.411 if I round to 3 sig fig, and because 0.411 is greater than 0.005, which is our 5% significance level, that's another reason for why we do accept H0. You don't need to give both reasons, you only need to give one of them. Sometimes you won't have the critical value, so you're going to have to use the p-value. Other times you won't know the significance level, so you're going to have to use the chi-squared and critical values. It just depends on the question. In this case, we were able to do it either way. And so your final conclusion, therefore, gender, you have to include this conclusion, by the way. It's important you do finish off the question. Therefore, gender and subject choice are independent classifications or factors or variables, whichever one of those three words you wish. Okay, question number 6. A group of 15 students was given a mathematics test and they then played a computer game. Here are the scores on the test and the game. And you'll notice that the mean point, which is the average of all of the x's and the average of all of the y's, has been conveniently given for us. So what do we have to do in this question? So there's the mean score, 56.9, and the computer game 45.9. Yes, that means the point M has got those coordinates. Okay, describe the relationship between the two sets of scores. So let's look at the scatter plot. It appears that there's something of a negative correlation, meaning that the better you did as a mathematics score, the lower your game score was. And the higher game scores, people who are good at video games, tend to be not so good at math. That's not surprising. They're probably spending all that time playing games and not doing math homework. So let's have a look. I'd say then this is going to be negative correlation because it's going downwards. How strong? Maybe moderate? I don't know. It's a tough call, really. It doesn't look super strong, but it's certainly not super weak. I'd say moderate to maybe even moderate strong. So let me write moderate strong negative correlation. Okay, a straight line of best fit passes through the point 0, 69. Where's 0, 69? It's right here. So we have to then draw a line of best fit that passes through not only that point, but it must go through the mean point. And so I'll do my best. You would use a ruler or the edge of your ID or calculator, I hope, but that's not a bad attempt at a